yes, I'm Jo, and I'm a teacher and a research scientist by background, and I've spent more than 20 years working in science education, both with primary and secondary, and in fact all the way up to university education as well. But I really focus on those kind of middle years, so the primary going into secondary school, or the middle school programme as well. I run lots of fun and engaging hands-on workshops for children, really trying to improve that science inquiry and opportunities for investigation. But I also spend a lot of my time supporting teachers with professional development as well. And I work through it with a range of organisations in the UK. So it's good afternoon from the UK, but good morning to those of you joining us from the States, and good afternoon, good evening to those of you joining further east as well. It's really lovely to see all of these names and locations popping up in the chat box. So thanks very much for taking part in that. So we're going to be doing some fun and engaging hands-on science this afternoon, this morning, this evening, wherever you are. So if you've got the activity, the resource list with you, you can join in, but also feel free to have a go at some of these activities later on as well. And we'll be seeing from our active participants some of the hands-on activities that I've got to show you today. So I'm going to be signposting and showcasing some activities. So we'll be having a go at some really low-tech resources. You don't need to have a fully equipped science lab, although it's lovely if you've got one, to do meaningful science inquiry and investigations. But I'm also going to signpost you to some other resources, so other places that you can find things from, and kind of a higher tech version of things that happen too. So first of all, I'd really like to hear your thoughts on why we might do practical science. So why do we do hands-on investigations? Why do we add that practical to the knowledge base that we teach students as well? Now, if you can, I'd really like you to visit a Jamboard, a collaborative board I've put together. So Shraddha, if you could put that into the link on the chat, that would be really great. For those of you who've got a QR reader on your phones, you might want to just waggle it in front of the screen here, and it should take you to a Google, oh, I can see people are popping up already. So if you haven't used the Google Jamboard before, it's a really lovely kind of interactive way to get lots of people's ideas straight away. You can either select a text box and pop things in, or as I can see people are doing already, you can kind of stick a little sticky note, choose a colour, and add some things on there. So down the left hand side, you'll see there's a menu. You can select either kind of, it looks like a little sticky note or a text box. So I can see people are popping up ideas like practical science is all about authentic learning. Absolutely. It makes it memorable. Children are using all of their senses. Motivational, absolutely, encourages students to observe, to think, to reflect, to be curious. These are all the reasons why I love my job. Encouraging critical thinking, building inquiry skills. Lots of ideas popping up there. Fantastic. It's relevant, absolutely. It needs to be relevant and meaningful for our students, doesn't it? Problem solving, yes, really crucial skills. Making it fun, absolutely. Learning should be fun, shouldn't it? Yeah, giving children the chance to hypothesize. Some brilliant ideas popping up there. If you could keep adding those in, that would be great. And then this link will remain live and accessible for you, so you can keep accessing this Jamboard as well. Some fabulous ideas popping up there. And hopefully the ideas that you've all come up with reflect what we've got in place here. So the Gatsby Good Practical Science Report from 2017 has identified that there are 5 purposes of practical science. So it's to teach the principles of scientific inquiry. And I've just spotted here that I've spelt inquiry the British English way, and there's a lot of American English spelling of inquiry, so both are valid, it's all fine. So in order to teach the principles of scientific inquiry, to improve the understanding of theory, to teach those specific practical skills as well, actually, how we measure things and observe. So lots of key skills that need to actually be taught as well. motivating and engaging as well, to make that learning fun, and also to develop those higher level skills that you've mentioned, some of you on the Jamboard as well, like communication and teamwork and perseverance and problem solving, things like that. So this is kind of the 5 main areas, but obviously there are many reasons for actually doing practical hands-on science as well. On that same link on the Jamboard, if you flip to the next slide, so right at the top there's a little box that says 1 of 4. If you click the right arrow, it'll go to the next slide on that, which is about the challenges that you might face in terms of being able to provide opportunities for practical science.
Joe, I think a few people are having trouble accessing the Jamboard. So a quick thought, maybe those of them who can use it can do it, but the others can maybe just pop their thoughts into the chat and you could look at that too. Okay.
Pop them in the chat, then we can have a look at those too.
Thanks,
so
Joe.
Feel free to either pop in the whys or the challenges that you face. And I'm just going to see if I can pop over to that. So I can see some people have found that board already. So challenges from for engaging in practical, limited time. Absolutely, time is our biggest challenge in education, really, isn't it? Limited funding, absolutely. Well, hopefully, I'm actually going to show you some ideas today that really won't require a huge amount of funding, but I'm not going to be able to magic you any more time, I'm afraid. Time and space, time for children to continue and extend the learning. Absolutely, that's always a challenge, isn't it? Having enough opportunity and time to fit that in so that children can discover things for themselves. Safety, absolutely. It's really important to make sure that any activities that we do, children are safe. Materials might not be available. Distance learning absolutely can be a challenge. So again, hopefully I'm going to show you some ideas today that you can use for children accessing education from home currently in the current situation. Time to plan. Let's just have a look at the chat as well. Yeah, really tough to teach hands-on practical science online. Yeah, lots of online struggles there. And wanting to minimize screen time as well. Well, again, hopefully I'll show you some ideas and activities that children can do some independent investigations with at home as well. Well, that's really nice. So there's people setting up laboratories in school too. Too much screen time. I don't know if there's a non-Google version of the Jamboard for use in China, I'm afraid. There might be something that you can access, but if you, Katrina, if you can just type any things you've got into the chat, then if we can save the chat at the end, I can add them into the Jamboard later on, and I can potentially share a link of that in a different way for you. So lovely ideas popping in about yeah, Padlet might also work in China. Absolutely. Thank you, Donovan. That's a really useful situation. Yeah. Padlet has lots of similar features. It does. Okay, so, and it's interesting to see that, people participating from all sorts of different places around the world, and the same challenges are popping up about time and resources, and having that ability to let children have the opportunities for exploration and discovery. So let's get on with some of those ideas then. If you would like to join in with the activities that I'm going to signpost today, then you will need some glasses, a jug of water, a metal spoon, something like some raisins or dried cranberries or even dried lentils or rice, a bowl, some paper and some scissors, and you should be able to join in with the ones that my active participants are going to be doing as well. And then hopefully you can jot down some ideas for some of the others that you might like to have a go at too. Now, whilst the primary curriculum is not really divided into biology, chemistry and physics, a little bit more so at middle school, I have divided the activities I'm going to showcase to you into some that fit within the physics, the biology and the chemistry strands of the science curriculum. So in terms of the physics, we're going to be focusing on sound, we're going to be looking at plants and the biology strand, and at the properties of materials in the chemistry strand. So hopefully there's something that touches lots of different year groups within those curricula as well. So when we think about sound, first of all, things that we're trying to get the children to notice and observe are that sound is caused by vibrations, so by something vibrating or shaking, and that it moves, it travels in waves, and that it can travel through different media, so through gases like the air around us, through solids, and through liquids as well. So a really easy and simple, really nice starter activity for exploring different aspects of sound is something that you can really easily do with a selection of glasses and some water. So I'm going to ask my active participants to pop their videos on now, and they are going to join in. They've got some glasses with differing amounts of water in them. So some of them have got a very little amount or none, all the way up to kind of an almost full glass as well. And I'm going to ask them to tap their glasses in turn. And I'd like you, and we'll just use the chat function for this so that everybody can participate, to pop in the chat what you think will happen, what observations could be made, and then maybe some whys as well. So we're going to be exploring the pitch, so thinking about the vibrations. So in the chat box, so different sounds, excellent. If you could add some thoughts while you can see the demonstration happening here, as they're tapping their glasses. What do you think is happening? So that you can hear loud to soft sound, okay, different sounds.
Jo, do you want them to unmute themselves?
It might be nice if we could hear your glasses too, but it might be a slight cacophony of noise. So we'll have a go. Less water, different pitch in the sound, excellent. So we've got some thinking about, frequency of vibrations, different sounds from the different levels of water. Fabulous. So Rochelle, I can see that you've got a large selection of glasses there. Is there anything that you notice in your different sounds from one end to the other?
Well, the interesting thing is that it differs when you're using which end of the spoon as well. So I wasn't quite sure which end of the spoon I should use, but yes, this one sounds almost dead. And then we get lighter as we go along. I guess lighter is the right word. I'm not sure. Higher, maybe.
So it also will make a different sound.
Scientist.
Will make a different sound whether you tap it on the top and the side as well. I don't know if you've explored that. So it kind of sounds a bit more musical if you tap the side of the glass. So tapping between different sides of the glass feels lighter with less sound. Yeah, so connecting to patterns, absolutely. So there's lots of pattern seeking in this. So we're showing, the pattern that changes between the amount of water that you've got going in there. So the glass thickness will also change the sound, absolutely, which is why I had asked my lovely volunteers to try and get the same glasses, so that they so that if the glasses are the same size and the same thickness as much as they can be. I mean, you can also explore it differently by having a range of different glasses, but put the same volume of water in them and see what happens. So yeah, it depends which variable you want to be controlling. So the glass full of water causes the glass to vibrate slower, and the sound you hear is a lower pitch. Absolutely. So we've got some lovely scientific explanations coming out there as well. But actually all observations are valid as well. As long as the children can explain why they think something is happening, that's a valid observation, isn't it? So I've just got, thank you very much, my lovely helpers. I've just got a little a demonstration video to show you so that you can see it kind of close up. So I've poured almost a full glass in one, about half a glass in the other, and about a quarter of a glass. And then I've left one empty as well, because actually it's good to see that it's not just the water that's causing it to make a sound. Hopefully you can hear the difference between the different glasses, but certainly between the first and the last. That's just my attempt at being slightly musical. It's not one of my skill sets, unfortunately. So this is exploring the differences in pitch, as we've been popping in the chat as well. So what's happening here is the glass is vibrating when we tap it with the spoon. And the amount of water in there depends on how much it's dampening those vibrations or stopping the glass from vibrating. So the glass that's empty or with a very little amount of water in it, the glass can vibrate really rapidly, so at a higher frequency, causing a higher pitch. The glass that's full of water, there's not so much glass available to vibrate because the water's dampening it, so it vibrates more slowly and thus causes a lower pitch. Fabulous. Excellent. It's really lovely to see your comments popping up in the chat box as well. Now we can explore this in a slightly different way as well by actually using bottles instead of glasses and filling them with water. Now you can fill the bottles with water, the glass bottles with water, and tap them with a spoon in the same way and you'll get a similar result. But if you blow across the top of them, you'll actually get the opposite effect. So this is a really interesting one to get children to observe and wonder why those differences are happening. So in the case of this, when you're blowing across the top, what's actually vibrating here is the air inside the bottle. And so if you've got an empty bottle or a bottle with not very much water in it, there's a lot of air inside the bottle. And so the vibrations are very slow and it produces a lower pitch. If you have a bottle filled with water, then there's not much airspace left in the bottle. So when you blow across the top of it, it's got faster vibrations and a higher pitch. So you get the opposite sound. So again, thinking about those patterns and the differences between them can be a really interesting way of exploring this with children. Yes, and you can turn it into a water xylophone and play a tune. You absolutely can, if you're more musical than I am. But another lovely thing for children to explore as well. And actually we can make musical instruments from all sorts of things. So you can just find objects around the classroom, around the house that make a noise. And it's a really useful way for children to explore what might be making the noise. So what's vibrating in different cases. So it can be a cardboard box that you bang with a spoon, or you could actually stretch an elastic band over it, different thicknesses of elastic bands or different tightnesses. And that's basically a guitar. So you could be, make different tightnesses of strings, so you get the different pitch happening. You can turn all sorts of things into a musical instrument. So just kind of doing a scavenger hunt can be a really useful thing to find lots of things around the house or the classroom as well. So yeah, just getting children to think about what's vibrating in different objects as well. So how it's making that noise. We can also visualize those vibrations as well. So if you get a bowl and you stretch some plastic wrap over the top of it so it forms a really tight skin, and you can also do this on a drum as well, because it's basically forming a drum, and then you put something like some dried rice or lentils or glitter works quite well, or powdered paint, and then you make a noise really close next to it. So maybe get a metal tray and bang it. Then the vibrations nearby will cause the rice to bounce on top of the drum. You can also kind of do this if you've got a speaker and you lie the speaker on its side and put some cling film across the top of it and turn the speaker volume up, and then you'll get, as the music's playing, you'll get the things bouncing on top of it too. And if you do it with powder paint, you can make some art with it as well. But that's definitely one to have in a space that doesn't mind getting dirty. Yes, with a Bluetooth speaker inside, absolutely. Yeah, lots of fun to be had with this one. So it's a really nice way to visualize those vibrations as well. So yeah, you can do it really low tech just by banging something next to the bowl, or you can make it really high tech by using a speaker or even your mobile phone playing some noise inside there, so they'll see it vibrate. There's the classic paper telephone string telephone that you just need a paper cup for. So you just make a hole in the bottom and stretch that. I'm hoping you can see that. Stretch the string between the two, and then you can talk in one end and listen to the other, keeping that string tight. And it's a really nice way of exploring that sounds can travel through different objects as well. So it's traveling through the string in this case. There's another one that you can do with a small cup and a slinky or a spring. So again, a hole in the bottom of the cup, add the slinky or the spring, and it makes a really cool noise. It sounds a bit like a lightsaber. So if you have any Star Wars fans in your classes, that's a really good one to have. So lots of ideas for teaching sound, kind of on the physics side of the curriculum. Now let's have a look at some plants as well. So wherever you are in the world, there will be plants growing of some sort, and at most times of the year as well. So here in the Northern Hemisphere, there's not an awful lot growing at the moment. And those of you joining us from places like Canada, I'm guessing everything looks kind of white and snowy, but hopefully there might be tiny places, or, you know, at certain times of the year where you can find things growing. So we can use plants to reinforce all sorts of scientific skills, like identifying, classifying, grouping, observational drawing. So, you know, there's lots to be gleaned from being able to observe what you can see and translate that into something on a page. You can think about habitats, so where the plants are growing, what adaptations they might have to be able to survive there. So you could compare plants growing in your local area with ones that you can see from around the world. So lots of secondary research you can do there as well to research what grows elsewhere, but also within microhabitats where you are, what grows underneath the shade of a tree versus out in the middle of a field, or what grows near the beach if you're lucky enough to be near the shore, compared to further inland. So lots of opportunities to explore all sorts of things and look at the characteristics that the plants have. And obviously that can be done with animals as well in those areas. Yeah, pine needles, pine cones in Canada at the moment, absolutely. And you'll see some of those pop up in a little while. So thinking about that observational drawing, there's lots of things you can do just to look at the, you know, from very young children, looking at the structure of a plant. You know, there's a flower and a stem and leaves and roots usually. But you can also then take a closer look at the flower part and think about the life cycle of a plant. So again, bringing in those pine needles and pine cones from the Canada example there. So you can look at the parts of a flowering plant. And there are all sorts of, I've just come back to that, sorry, all sorts of different plants that you can use. Just make sure that whichever plants you're using from where you live, that you make sure that none of them are poisonous. But there are plants that have got really big flower heads are the best ones to work with because they're easy to see. You can just slice them in half, or you can even get the children to pick the different parts apart and have a look at the different bits of a flowering plant. The seeds of a plant are really interesting as well. So again, we can use these for identifying, classifying and grouping. Children can think about grouping them in all sorts of different ways, what they look like on the outside or the inside, or perhaps even the way that they are dispersed as well, so that they're sent around. So obviously the apple here is relying on an animal to eat it and then deposit the seeds somewhere else in a pre-fertilized little package. The pine cone works by pinging open when the humidity is kind of the correct temperature, so it flings the seeds far and wide. Coconut is going to be relying on water to transport it, so they, you know, go into the sea and float between islands. And the bottom right there, you might not be familiar with if you're not in the Northern Hemisphere, but is a horse chestnut or a conker, and they come in a little a casing, which is, I suppose, cushioning them, but it's got spiky bits on it as well, so they kind of bounce when they fall and then travel a further distance away, but the spiky outside stops animals from eating them when they're not ready. So yes, exploding seed pods are really fun to explore, absolutely. So lotus seed pods that float on the water, they're quite cool. Poppy seeds that fly out, and in fact you can use plastic water bottle, an empty water bottle, make a little funnel in the top and pop little pom-poms or just screwed up balls of water, and then pop the sides of the water to model that exploding seed pod action as well. It's quite a fun one to do. So lots to do with seeds as well. And obviously the really cool ones that blow on the wind, so the wind dispersed seeds as well, like the dandelion clock. There's also lots to explore in terms of growing with plants. So thinking about the conditions that plants need. Do they need light? Do they need water? Do they need nutrients in the soil? Can you set up a comparative experiment with putting plants in different places? Just looking at the changes over time in terms of planting a seed and watching it grow, or indeed watching a plant turn into a flower, observing seasonal change. So looking at the trees when they've got leaves on the tree, when they've got flower buds, all sorts of different things like that. We can also explore how water transport happens in plants as well. So looking at capillary action, so the water being travelling up the xylem and the phloem inside the stem of the plant. So a classic one to do is to pop some white flowers in some coloured liquid, and then as that capillary action happens, you see that the white petals turn the colour of the colour that you've put in the water. So these are carnations, they work really well, but celery also works quite well. And people often struggle to get this one to work. I would say you either need a really, really lot of food colouring in there, or my top tip is actually don't use food colouring. Get a felt tip pen, so a children's colouring pen, and then if you stamp on them, running down the middle is a felt covered in the dye, in the ink, and if you pop that in the water, actually it works much more effectively than using food colouring. So that's a really visual way to show that water travels from the bottom of the plant up to the top as well. Fabulous. So looking at capillary action and water transport in plants. And we can also explore capillary action in a hands-on way. So I'm going to ask my active participants to show their screens again now, because what we're going to do now is think about the action of water causing a movement, so filling up the gaps between bits of paper in this case. So if you're joining in along with this one as well, we've just cut out some paper flowers. I can see Nikki's beautiful yellow paper flower there. We were just discussing this earlier actually. So you can set up an investigation where you compare different types of paper and look at the different gaps that there might be between the paper. You can make different shaped flowers, all sorts of different things. So what they're doing now is they've cut out a flower shape and they're just going to fold the petals in. So it's a folded up flower. So folding one on top of the other. And then they're going to pop it on top of their bowl of water. So I'd like you, if you wouldn't mind, to just pop in the chat what you think might happen when they pop them in the water and why. So nothing popping in the chat just yet. They're hovering over it. So somebody thinks it will float, somebody thinks it will sink. Lots of it will open. So let's have a look, shall we? Rachel, Rochelle. Oh, that. Thank you. That's a beautiful angle, Rachel. You can see that working really, really well. So you can see we've got some different types of paper here as well. I can see there's just, Rochelle's got a bit from a notebook. Fabulous. Nikki's, I can't quite see if yours is opened yet or it's got itself stuck.
It's going slowly, slowly.
Going slowly, slowly. So this is a really nice one actually to bring in some of that observation and comparative as well, to see which ones open the fastest. Excellent angle, Rachel. That's brilliant. And it's doing it beautifully slowly for us as well. So similar to the toothpick experiment is a little bit, I'm assuming you possibly mean the one where you float it on the surface of the water and then you pop a little bit of soap on and it moves the toothpick. So what's happening here, lots of people, blooming flowers, absolutely. Lots of people coming up with great things in the chat. What's happening here is that the gaps, the gaps between the fibres in the paper are absorbing the water through capillary action, and it's expanding basically and forcing the flower to open out. So this is how you'll see leaves opening and indeed flower buds opening as well. So when they're first formed, actually that capillary action dragging the water up from the bottom of the plant all the way through to the ends is acting in a similar way to this. So quite a fun one. Quite a fun one to do as well. And as I say, you can extend this one with comparing the different types of paper and different sizes of flowers and things like that. Let's have a look at some chemistry now. So there's, oh, I see, the bending the toothpicks to make a star. Absolutely, sorry. Yes, I've misunderstood the experiment. Let's have a think about some chemistry. So thinking about the properties of materials, but specifically thinking about reactions and reversible changes and irreversible changes, and the physical properties that different solids, liquids and gases might have, and the changes of states between them as well. So I've got another one for you to join in with now. So if my participants could pop their videos back on. You may have seen this one before, and this is a dancing raisins experiment. So we're going to need a glass and a fizzy drink for this. So it works really, really well. What we call in the UK lemonade, but I know that in the States lemonade is not fizzy. It's not a carbonated drink. So something like Sprite or 7-Up or club soda or tonic water or even just sparkling water actually work really, really well. So with the children, what I usually get them to do with this is to start observing actually what's happening to the bubbles in the glass of the fizzy drink before they do anything else. So thinking about where they are. And you should see that the bubbles will be along the bottom of the glass and perhaps up the sides as well. And that's because the carbon dioxide is dissolved. I can see slight floods happening, is dissolved inside the water. And then there are nucleation points where there are slight imperfections on the side of the glass. And that's where that kind of seeds the bubbles. So it causes them to come out of the solution. You see lots of fizzing happening. You can also do this if you don't have a sparkling drink. You can do it with an acid-base reaction of some vinegar and some bicarbonate of soda, and you'll cause those bubbles of carbon dioxide to be produced. So I can see actually that Rochelle is doing it indeed in this way with the sodium bicarbonate, and I think Rachel might be too, judging by the amount of bubbles that we've got going on there. Excellent. So in itself, actually, the acid-base reaction of the sodium bicarbonate and the vinegar is a really useful one to do with children, to get those observations and to say that, you know, you've taken a solid and a liquid in that case and put them together and you've formed a new product, you've formed a gas. So there's lots of things to do with that one, following on from that. So observing the bubbles, whether you've got it from a can of fizzy drink or from your sodium bicarbonate and vinegar reaction. And then you just need a couple of dried raisins or dried cranberries, something small. And if you pop them just 1 or 2 in and observe what happens. So having a really close look at those raisins and thinking about where the bubbles are again. So we should be able to see that what's happening is the bubbles are starting to gather around the raisins. Oh, and I can see Nikki's are starting to move. So they kind of attach themselves, just like I mentioned the nucleation points on the side of the glass. The surface of the raisin has got these imperfections on it, and it causes the bubbles of carbon dioxide to seed there. And so when enough of those bubbles have collected on the raisin, it's a bit like balloons lifting something up. So in fact, actually, I should have moved to the next slide to get you to pop what you think is happening in the chat and why. So there's lots of people who have preempted me there. So yeah, the bubbles surround the raisin and make it lighter. So yes, so technically it's making it less dense when they're combined than, yes, so it's rising up, absolutely. So the raisin goes up. And then what you should also be able to see, so the bubbles are acting a bit like balloons lifting the raisin up, is that when it gets to the surface, what happens? and then they release, it bursts. Yeah, absolutely. So the bubbles pop when they get to the surface, which means that the raisin is then more dense than the liquid it's in, and so it sinks back down. So this is a really good one actually to get children to slow down, to focus and to observe, and to really think about what's happening. And I often use this one as a precursor to then a much more kind of explosive version of this, which is getting a bottle of a fizzy drink, usually a cola or something like that, and dropping Mentos sweets into it. And what happens is that they act as that nucleation point, much like the raisins, but because they're in this kind of tight enclosed space, they come out in a soda fountain. So soda fountain, hugely popular, very exciting for children, but I find that they're not focusing on the science and what's happening when they do that. So using this one with the raisins, the dancing raisins first, really helps them to focus on what might actually be happening. Yes, so the Cartesian, fabulous, archaeological divers using it for bringing things to the surface. So using bubbles to bring things up. So I absolutely love, Sandra, that link between what's happening, what we use in real life science and exploring those properties of materials. Yeah, floating and sinking, lots of ideas around that. Fabulous. Excellent. I love that example. Thank you so much. And thank you to Rachel, Rochelle and Nikki for demonstrating your raisins there. So I've just got a little close-up video now of this is some vinegar, and I'm just going to pop some raisins in. So again, you could start with this way. The raisins have just sunk to the bottom when I've just got the vinegar in there. But watch what happens when I sprinkle some sodium bicarbonate on top. You can see the bubbles of carbon dioxide forming, and hopefully you can just about see them on the surface of the raisin as well, and lifting it up, and then they go back down. So the bubbles pop on the surface and it goes back down. And often the children like to have a competition about whose raisin moves the quickest or the first or the most times. So and then you start to get experimentation as well of what can they do to make, is it the bigger raisin or the smaller raisin? So again, that pattern seeking that floats and sinks the most, or is it the one that's the most wrinkled or the least wrinkled? Lots of things going on for observation in this. And if you don't go on and do the explosive soda fountain afterwards, then actually it's quite a calming activity as well, which can be really useful sometimes. So yeah, you can use that acid-base reaction with the sodium bicarbonate and the vinegar, or just go straight for the fizzy drink. So using the idea of things that you can do in a glass and taking that further as well, there's lots of things we can do this. We can dissolve things, so thinking about solutions and whether solids can be dissolved in a liquid or not. So you could do all sorts of things like sugar and salt, which will dissolve obviously, but what if you put sand in, or soil? Bits of the soil might dissolve, but bits of it might be held in a suspension. So you can look at the differences between solutions, mixtures and suspensions as well. So you could do this with water and with salt or with sugar. And then you can also then extend that further and start thinking about density as well. So the egg that's at the bottom here is just in a glass of water, but the egg that's floating is in a glass of water that's had several spoons of salt dissolved in it, which makes the water more dense. So the egg is able to float. It's the same egg. So, oh, excellent. And people are popping in some links in the chat as well. So we can explore density as well as solutions. And you can extend that density even further with different liquids as well. So can you float the oil on top of the water because the oil is less dense? You can, use different things like honey or syrup, all sorts of things like that. Thinking about the different densities of liquids. We can then take that solution that you've made by dissolving salt into the water and evaporate it actually, so we can separate things out using that solution as well. So, and you can look at things like what variables that have an impact on evaporation as well. So the temperature, the relative humidity of where you are, and the airflow as well. So you could get the children to set up these experiments in different places. So in a sunny spot, in a cool shady spot, on a radiator, if you know, on a heater, if you're somewhere really cold as well, and look at the differences in the rate of evaporation. And you can also compare salt and sugar. So this is a salt solution. You can see that the crystals are kind of a square-based pyramid, and sugar crystals form a different shape. So you can look at the different shapes of the crystals that form as well. You could even then separate solutions in a slightly different way. So you could get the children to actually make a mixture of all sorts of different things. You can put rocks and soils and leaves and dissolved coffee granules and salt and sugar, and can they separate out all of those different things using different techniques? So filtering and sieving, and you can do that using just an empty plastic bottle and a bit of paper towel to separate out some of the bits from that. And you can see that I've gone from a very dark liquid to a much lighter brown liquid. I still wouldn't want to drink it, but you can go on and you know, perfect your filter as well, and think about different materials you could use, and what you could do, and then think about how to get out the salt if you've popped salt in as well, to using evaporation as your final. Yeah, lots of salt. Yeah, so you can use the image of salt flats. Or if you are lucky enough to live by the sea, go and have a look at some rock pools and you can see the salt crystals around the edges. So lots of things to do with that as well. So we've had a kind of a whistle-stop tour today of a bit about the what, but lots of the why as well, and some how of doing some practical science without using really any equipment. All of the things that I use, you can find, you know, easily around the house or in your school. So we thought about the whats and the whys, and I just wonder if you can reflect back on the input that you had at the beginning on why we do practical science, and think about whether anything has changed. Have you thought about other reasons that we might do practical science? Is there anything different? And feel free to keep adding to that Jamboard as well. I can see lots of people posting ideas in the chat as well. So just to bring us back to that summary of the 5 purposes from the Gatsby Good Practical Science report, of why we do practical science. So we've looked at teaching principles of scientific inquiry. So hopefully some of those investigations I've shown you today will prompt ideas of how you can then use that to promote inquiry in your students as well. And lots of ideas in the chat as well about provocations that you can use to get your children questioning and thinking. We've also need to do practical science to improve understanding of the theory through practical experiments. So we can absolutely teach instructively, and children have that knowledge, but we know that learning by doing is well, it's a much more fun way of doing things, but it also helps to embed that knowledge as well. But also teaching those specific practical skills like measurement and observations, and for fun, because it's motivating and it's engaging. But also I think it's really important to value practical science because of the higher level skills that it supports as well, and cross-curricular skills too. So that communication and teamwork and group work that we like children to do. Obviously that's a little bit challenging for some schools at the moment, working remotely, but hopefully that's going to come back. And perseverance. Science doesn't always go the way you expect it to go. So you need to be resilient, you need to be persevering. And in fact, you know, that's the best scientific discoveries happen because people have found out something different to what they expected usually. So lots of reasons for doing it. Yes, experiences stick and have meaning. Yeah. Thank you. Thanks for joining me, everyone.